extrinsic semiconductor. So extrinsic semiconductor means it is a impure semiconductor. It is a impure semiconductor, or we can say that it is a compound semiconductor. So intrinsic semiconductor is a elemental semiconductor, pure semiconductor and intrinsic semiconductor. Extrinsic means elemental, means here it is a compound. Pure, here it is impure. Then intrinsic, extrinsic. Why it is called as an impure semiconductor, sir? So now we are going to add the impurity to the pure semiconductor. Then adding of the extra atom to the pure semiconductor is called doping. So adding of extra atom, that is a foreign atom other than the silicon atom or other than the semiconductor atom into the semiconductor material is called doping. So what will happen? The pure silicon material will have the one additional other than the silicon atom present. So we can say that the silicon is impure. So that is a impure semiconductor or the compound semiconductor or extrinsic semiconductor. So the doping means addition of extra atom. Let us we take the one atom, that is a arsenic. The arsenic is a pentavalent element. Arsenic is a penta means 5. So the outermost orbit has 5 electrons. So the silicon has 4 electrons. 1, 2, 3, 4. Again 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is a silicon. So now what we have to do? We have to remove the one silicon atom, then one arsenic atom is added. That process is called doping. Why we are taking the pentavalents, or even if you are higher valent elements are we are taking, means the size of the atom will be increases. Then when the size of the atom increases, the whole crystal structure displaces. The entire property of the semiconductor will destroy. So we can replace the another atom which is the same size as that of the silicon, that is just above. That is, the silicon is a tetravalent, this is a pentavalent. One electron is extra than the silicon, that is a arsenic atom. So arsenic, any pentavalent atom is a similar size of the tetravalent element, because the only one electron is extra. So for the arsenic, how many electrons are there? 5 electrons. 1, 2, this arsenic atom make a covalent bond with this silicon atom. Here the covalent bond, here the covalent bond, here the covalent bond. Then what will happen? Only 4 electrons have the nearby silicon electrons pair make a covalent bond. But the 5th electron, what will happen? It will be in the ready state to liberate as a free electron. So this is having a no bonding, no covalent bonding electrons. So whenever what will happen? So at very low temperature, this electron may become a free electron. Then what will happen? Here the vacant will be created. That vacant is a hole. Are you clear? So very simple. So I will represent this one as a in the valence band diagram. So what will happen in the arsenic? All the outermost orbit electrons are occupied in the valence band. Dear students, I am sorry to say this. This is the silicon. The silicon atom electrons only occupied in the valence band of the silicon atom. But where is the valence band of the arsenic atom? Arsenic atom valence band is, or the energy level is, lies here. So arsenic atom valence band is lies here. So that atom has the extra electrons here. So this what will happen? This electron will at very low temperature itself, this electron will jump up. So this electron will jumps to the conduction band. Even at 0 Kelvin, at T is equal to 0 Kelvin itself, what will happen? The silicon remaining system, here what will happen? Another silicon atom, silicon goes on. Only the impurity, the concentration of the arsenic atom is very small. The doping concentration must be very less. That is 1 parts per 1 ppm, 1 parts per million. For 1 million silicon atom, for 1 million silicon atom, only one arsenic atom has to be added. Otherwise, if you add more arsenic atom, this material will become an arsenic material. So the semiconductor means it is a silicon or germanium material. So what will happen? We have to add the very less number of dopant material, that is a dopant atom, that is a doping atoms arsenic. So what will happen? So the blue color is a silicon. The silicon electrons are bounded in the valence orbit itself, so we can represent in the valence band. But this is the arsenic atom. Arsenic atom is a donor atom. It will donate the electrons. So this is a donor level. So the donor atoms are occupied here only. So donor atoms are occupied here only. What will happen? This atom liberates electrons, free electrons, to the silicon crystal. Then what will happen? This arsenic atom will become positive ions. This arsenic atom will become positive ions. Are you clear? Then what will happen? When the temperature T is greater than 0 Kelvin, that is it will be around 300 Kelvin at room temperature. What will happen? In this other crystal structure, few covalent bonds are breaks. Then what will happen? The electrons, these valence electrons will come to the conduction band. So what will happen? The number of holes in the valence band is not equal to number of electrons in the conduction band. Here the number of electrons in the conduction band is greater than number of holes in the valence band. Hence more number of electrons are there. Electron is a negative. So this is a negative type semiconductor. That is simply we can say N-type semiconductor. So I will explain one more time. In the pentavalent atom is added means one electron is ready to liberate out, because there is no other silicon electrons are having pair with this fifth electron of the arsenic atom. So the energy level diagram will be like this. So the valence band of the silicon atom is this two one. So this is the donor level, arsenic energy level. So the arsenic atoms are occupied here. The arsenic atom makes a bond with silicon atom. The only one electron is ready to liberate out at even at approximately 0 Kelvin, around 0 Kelvin, 10 Kelvin and 15 Kelvin itself. It will liberate the electron as a free electron. So we can say that what will happen? This electron will jump to the conduction band. Free electrons are always occupied in the conduction band. So whenever the electrons are coming out, this atom will become ion. So positive ions are there. Then what will happen? When the temperature increases to room temperature, as usual few covalent bonds are breaks. The valence band electrons will come to free electron, that is a conduction band electron. There will be a more number of electrons compared to more holes present in the valence band. Hence more electrons means more negative charge. More negative charge means negatively charged semiconductor. So that is a negative type semiconductor is called as a N-type semiconductor. Similarly, for P-type semiconductor, we have to use trivalent element. So trivalent means 3. Outermost orbit has only 3 electrons. So the silicon has 4 electrons. All the silicon atom has 4 electrons in the outermost orbit. Then boron is a trivalent element. So it has a 1 electron make a bond with this silicon atom. The another electron make a bond with this silicon atom. And then another electron make a bond with this silicon atom. Okay. This silicon atom. Then what will happen? So these 3 are the silicon atoms. So this silicon atom has no electron. So the boron has no electron available to contribute to this silicon atom, make a covalent bond. So what will happen? There will be a vacant created. That vacant is a hole. That vacant is a hole. So here what will happen? Extra holes are available. So how you are represent this? The valence band means the silicon atom valence electrons are completely filled. For the boron, this is a donor level. This is the donor level. Sorry, this is the acceptor level. So the boron atom is ready to accept the electrons. If anybody give the electrons, this hole will accept this. So this is called as a acceptor level. Acceptor energy level. So here what will happen? This acceptor energy levels have the extra holes here. How many boron atoms are there? That much holes are available. Then at very low temperature, at T is equal to 0 Kelvin itself or around 0 Kelvin itself, what will happen? These electrons may jump to this boron atom crystal. So what will happen? Here it will be occupied. If it is occupied means the boron will become a negative ion, because when the extra negative charges are added, so this boron will become negative ion. Here the holes are created at T is equal to 0 Kelvin itself. When the temperature increases to 300 Kelvin, what will happen? Other covalent bonds are breaks. Then it will be jumps to the conduction band. Are you clear? Again I will say that this is a conduction band. So at T is equal to 0 Kelvin, the boron has an extra hole. So the extra hole is energy level is available here. So this is a acceptor energy level. So at very low temperature, this electron will jump here. Then this electron jumps here. Likewise it will goes on. So the electron will jumps to the boron atom. Boron atom absorbs the silicon atom valence orbital electron. Then the boron atom will become a negative ion. So the negative ions are present here. Then what will happen? Automatically in silicon atom, the holes are created at 0 Kelvin itself. When the temperature increases to room Kelvin, so the electrons are jumped to the conduction band. Then again here the holes are created. In this case, the number of holes is greater than number of electrons. Holes is a positive charge, electron is a negative charge, hence it is a positively charged semiconductor, so we can name it as a P-type semiconductor. So when the trivalent is a dopant material means P-type semiconductor, pentavalent means N-type. You can remember that is a tetravalent. 4 elements are there. So 4 plus 5 it is a 9. So octant structure is 8 only. So there is a 1 extra electron. Negative charge is extra. So it is a N-type semiconductor. So silicon has a 4 electrons. Then boron, the trivalent has a 3 electrons. Total 7. So we have a 1 deficiency of electron, -1. That is, if you add 1 electron means then it will become a octant structure. So the deficiency of electron is called as the holes. So the holes are present means P-type, electrons are present means N-type. For the N-type semiconductor, the electrons also present, holes also present. P-type also electrons are present, holes are present. In N-type semiconductor, electron is a majority carrier, holes is a minority carrier. In P-type semiconductor, holes is a majority carrier, electron is a minority carrier. So in semiconductor, the current conduction is by both electron current as well as the hole current. But in conductors, pure metals, the electron only contribute for conduction of the material. But in semiconductors, both electron current and hole currents, the sum of the electron current and hole current is a total current of the semiconductor. So this is an intrinsic semiconductor structure.